Okay, Mark. Welcome, everybody. Welcome to our members and the members of Clydesdale Astronomical Society joining us on Zoom. And welcome to everybody else who's joining us on YouTube. Tonight, we have a talk by Professor Andrew Coates on looking for life on Mars. Andrew's the professor at the UCL and the Mullard Space Science Lab, and the principal investigator for the rover Pancam, all of which he'll talk about in far more detail than I will at the moment. This will be followed by Q&As, and we'll do that in the normal way. If you're on Zoom, if you'd like to put your questions on the chat line, Peter will ask individual people to ask those at the end of the session. And if you're on YouTube and you're watching live, can you put them in the comments section and we'll try and get them read out. When we've finished that talk and the Q&As, we've got our very own Alan Pickup, who's going to be taking us through the sky in November. So we've got a fairly full evening. Next slide, please, then. Well, I'd like to welcome 3 new members. Our membership continues to grow, I'm happy to say. Could we welcome Gary, Robert and Ewan in the normal way, if you members like to unmute? Welcome aboard. I hope you're watching now. If not live, then you'll catch up on YouTube. So this brings our membership to 127. And if you are interested in joining us, we've been very active since lockdown and continue to plan to do so. And you can find all the details about joining on our website. Next mark, please. And you can stay in touch with us both on the website, on Facebook, Twitter, and all our previous talks from the period of lockdown are on our own YouTube channel, so you can catch up with those as you wish. Thank you, Mark. And what's coming up? Well, on Wednesday the 11th, for members, it will be the Imaging and Observing Group. And a reminder, if you didn't know it, between the 14th and the 22nd of November, it's the National Astronomy Week, mostly focused on Mars. I think most of the activities are around Mars. You'll find details on our Facebook page and links on our website. Mark will send the usual email newsletter out. There's lots of events happening, and we will be trying to do a few ourselves. But of course, a lot of that might be weather dependent, so you'll just have to stay tuned. On Friday, the 20th of November, we've got Rebecca Higgett of the National Museum of Scotland. Some of you may remember Rebecca. She helped organise the Charles Piazzi Smythe seminar for the bicentenary. And we have, in fact, Andy Lawrence coming along that evening to do the introduction. So that should be an interesting talk about one of Charles Piazzi Smythe's contemporaries and somebody who helped him. Okay, Mark. So I'm going to hand you over now to Professor Andrew Coates for him to talk us all about Mars and what they're going to do there. Would you like to share your slides?
Thank you very much. Yes, so here we go. So just share this and hopefully we can go to full screen. Is that working?
Yes.
Excellent, thank you. Right, well, thanks for the introduction. So I'm going to talk about looking for life on Mars with the Rosalind Franklin rover. So you can see a picture of the Rosalind Franklin rover on the right-hand side there. So I'm principal investigator for Pancam, which is up at the top of the mast of the rover on the right-hand side. So a little bit first about what Mars was like 3.8 billion years ago and what it's like now. A bit about water and life, and then about the rover and some of the other missions to Mars as well. So, and I should say, we're funded by the UK Space Agency. Thank you very much for that. And that's our Twitter handle on the bottom left-hand side for you to have a look at. And so starting off with where else could there be life apart from Earth in the solar system? So these are the top candidates. So Mars at the top left there is, of course, one of the great candidates, and the main subject of the talk tonight. So about half the size of the Earth. So that half the size of the Earth meant that it lost its heat of formation more quickly than the Earth did 4.6 billion years ago at the beginning of the solar system. And that's relevant for some of the material later. But Mars, we think, could have been habitable about 3.8 billion years ago, and that's what we'll introduce soon. But some of the other places in the solar system where there could either be or might have been life, starting in the bottom left there, that's perhaps one of the likely candidates. So Europa, of course, one of the moons of Jupiter, about a quarter of the size of Earth, and underneath that icy crust, it has a subsurface ocean. And it's a salty ocean, and there could be the right conditions for life even there now. Enceladus at the top right, so the Cassini mission, which we were also involved with, found these water plumes coming out from the subsurface ocean, which is completely underneath the surface of Enceladus as well. So another icy surface, and underneath that the subsurface ocean. And of course, those plumes threw out material, and we were able, with the Cassini spacecraft, to sample those and see what conditions there are like, and to see that conditions might have been right there for life as well, might even be right now. Titan, this object here, of course, again, smaller than Earth, but quite large, in fact the second largest moon in the solar system, but it, of course, another moon of Saturn, and this has a nitrogen and methane atmosphere, and it has basically prebiotic chemistry going on in that atmosphere. So with our instrument on Cassini, we discovered extremely large negative ions, which are sort of precursors for what floats down through the atmosphere and coats the surface. But this is likely, it's very cold there, and although there is a subsurface ocean there as well, conditions are probably not right there for life at the moment, but it could be something which happens later on in the solar system's history. And then, of course, recently Venus, and then this amazing observation of phosphine in the atmosphere of Venus, which possibly is indicative of life in the clouds there, but of course what has been seen as phosphine is not the presence of life, but it's one of the biomarkers, and so that's put Venus back on the map for exploration as well. But these are all amazing objects, but Mars is the closest, it's the easiest to get to. We've got a lot of information about Mars, but all of the other targets are definitely worth exploring as well, and so these will hopefully be the target of future missions. So with Europa, the JUICE spacecraft, which I was in a meeting about today earlier on, this is going to be doing a couple of flybys of Europa, and also flybys of Callisto and Ganymede before going into orbit around Ganymede. So this is for launch in 2022, gets to Jupiter system in 2030, then eventually ends up in orbit around Ganymede in 2032. So this is looking for habitability in the solar system, or the Jupiter's moons. So Europa is one of the exciting targets there. So as I say, it's doing a couple of flybys, which will help to set the scene. Also, we hope that NASA's Europa Clipper will be going and doing many flybys of Europa as well in a similar type of timescale. And Enceladus, no plans for a return mission yet, but of course, with Titan, the Dragonfly mission is going there in the late 2020s. There are a number of proposals going on to maybe go and look at Enceladus in more detail again. Venus, currently the European Space Agency and NASA both have things in their funding pipeline for potential missions to Venus as well. But the community is very active in all of these areas, and these are exciting topics. But Mars, of course, is the topic of the talk tonight, and so this is the focus that we'll be talking about now. Okay, so the next slide shows what Mars was like 3.8 billion years ago. So it had water on the surface. There's been a lot of evidence for that, starting with the Viking mission back in the 70s, was the first to really sort of see signs of water having been on the surface, and this is by seeing outflow channels which is associated with water. And so this particular picture actually is from Mars Express, the European Space Agency's Mars Express mission, which is still there and still sending data back after 16 years in orbit around the planet. And water on the surface is looking at the orbiter images, that's indirect evidence for water on the surface at that time 3.8 billion years ago. So another difference about Mars then compared to now is that Mars used to have a magnetic field. So this is from Mars Global Surveyor. It's a map of the Martian surface, latitude and longitude there, and the colors show basically height. So this is from the Mars Orbiter Laser Altimeter. So we're going from the blue, which is relatively low regions on Mars, through green and yellow, eventually red, and then white are the highest regions. So Olympus Mons here, the Tharsis region, volcanoes. But we see, in the North Pole of Mars, we have a sort of relatively low environment. There's also the Hellas Basin here in the Southern Hemisphere as well. But the Southern Hemisphere is much more, is much older and cratered. And from the cratering density, you can find that that is about 3.8 billion years ago, billion years old, that surface. But what's plotted over the top is magnetic field. And so Mars Global Surveyor was the first to be able to take a magnetometer to measure the magnetic field near to Mars. And it finds these, the contours basically, which we see, the black and white contours. These are outward and inward propagating magnetic field associated with crustal magnetic fields. So this is not a global magnetic field like the Earth has, but these are crustal fields left over from a time when the rocks were forming, and this is trapping the globe, remnants of a global magnetic field at that time. But that died out about 3.8 billion years ago. And one of the reasons it died out is that Mars lost its heat of formation more quickly than the Earth did, and so it became cooler. So the core motion stopped, which stopped the magnetic field being produced. Some people think also that the collision, the large collision which caused the Hellas Basin around about the similar time, that might have had a role in changing the energy balance in the system to be able to stop that magnetic field. So Mars used to have a magnetic field, it no longer does, and so since the time that the magnetic field was stopped abruptly, basically it's been possible for the atmosphere to escape via the solar wind. So that's a big difference of Mars then compared to now. So it had water on the surface, it had a magnetic field, which was helped to keep the atmosphere in. And it also had volcanism going on. So this is a better picture of Olympus Mons, the largest volcano in the solar system, so 600 kilometers diameter and 27 kilometers tall, so 3 times the height of Mount Everest. Very large feature. It's a shield volcano, and that's where it is on the map, and that's the we had that volcanism going on. So that would have contributed to a cycle of stuff going on at the time. So we think that Mars had an atmosphere a bit like the Earth at that time. It had water on the surface. And this is indirect evidence, though, that Mars perhaps was habitable at that time. Okay, so the next slide shows what Mars is like now. And of course, there was this amazing picture taken by amateur astronomers a couple of weeks ago. This one, and that was Damien Peach's picture. This one actually is one of the images from spacecraft, but Damien's picture is almost as good. Incredible picture of Mars, and of course that's visible in our skies at the moment. So Mars at the moment, though, it has, it's much. The volcanoes are extinct. There's no large-scale magnetic field, only these remnant regions or crustal magnetic fields. And it has a very thin atmosphere, so only 7 millibars, and that's variable during the day and also during seasons as well on Mars, but a carbon dioxide rich atmosphere, so certainly not habitable. It's also very cold and dry, and this is an image from one of the early rovers showing the the surface there. So cold, dry surface. And actually it's really cold. So at night on Mars, it's going down to about -100 to -120 degrees centigrade every night. And of course, during the day, maybe 0 to +10 to +20, something like that in a good area. But because of that thin atmosphere, it loses, that's not enough to keep the heat in. And so that at night we have these very cold temperatures. So any rover or anything we send to Mars has got to survive that cold night. And of course, the Martian night is just a little bit, or Martian day, the Sol is just a little bit longer than the Earth's day, at about 24 hours, 40 minutes. So Mars now, really not very nice, cold and dry on the surface, not habitable, very cold at night, but also because of that thin atmosphere, we can get radiation, cosmic radiation from the galaxy and from the sun down to the surface much better than at Earth. And so the radiation environment is significant on the surface of Mars, not a very nice, basically a harsh environment for life on the surface of Mars. Okay, so I mentioned some of the indirect evidence for water having been involved with the formation of channels and so on, the outflow channels that we see on the surface now. But with the rovers, it's been possible to get direct evidence actually that water was involved in the formation of the rocks. So this is from the Opportunity rover. So Opportunity landed in 2004, landed in a crater, and it landed in this crater which basically had sedimentary rocks there. So this, even from the first image, was an amazing discovery. This was the first time sedimentary types of rocks have been seen on Mars. So because it's a rover, it can move over to the rocks and do some experiments. And so one of the things it had on it was an alpha proton X-ray spectrometer. These are some of the results from that. So this is basically taking a radioactive source up to one of the rocks. I think it's over here, roughly the rock which they examined with this particular experiment. So you're taking a radioactive source and looking what comes off. So you get these big peaks associated with things like metals like iron, nickel, and zinc, which are shown here. But also much more refractory things, and so things which more associated with water. So things like sulfur, chlorine, and bromine, and those are much more associated with water having been involved in the formation of the rocks. The iron and nickel and things like that are not a surprise. The red color of Mars is partially due to iron oxides, and so that's not a surprise. But the beginnings of direct evidence for water were with this alpha proton X-ray spectrometer data. Also, the Mossbauer spectrometer, some of the results from that shown here on Opportunity. So this shows in this rock basically jarosite. So again, we have a radioactive source. In this case, it's moving backwards and forwards with respect to the target, and we're getting signs associated with particular minerals. And this one in yellow is shown the iron 3+ from jarosite. And so jarosite, the chemical formula for it is shown here with OH6 in that. And so that water involved in the formation of jarosite, the formation of the rocks at that time, involving water. So this is some direct evidence then now for water having been on the surface of Mars 3.8 billion years ago. So Phoenix, the NASA Phoenix mission in 2008, this landed near the North Pole of Mars. And it has this scoop, which you can see on the image here, that was able to pull away at the surface. This was a static lander rather than a rover, but it had this scoop, so able to scoop material up. So this was able to get a few centimeters underneath the surface. And what's shown on the right-hand side is images a few days apart. So first of all, there are these, you can see this is the shaded part of the crater on the groove on the left-hand side here. First of all, you see something, and then it's disappeared a few days later. And so that's why it's flipping from seeing something to not seeing something. And that's water ice just underneath the surface. So some water ice has gone underneath the surface of Mars from that time 3.8 billion years ago, when there was abundant water on the surface, clouds in the atmosphere, a climate a little bit like the Earth. at about the same time when life was starting on Earth, and so this is why people are interested to continue with Mars exploration. So this is showing just underneath the surface we have this sort of permafrost in the polar regions, and the signs of water definitely underneath the surface and in the images there. Okay, so more onto Curiosity, which is still there and working on the surface of Mars. So another NASA rover. So in this image, this looks a little bit like mudstones to a geologist, and this would have been mudstones 3.8 billion years ago. And by drilling, again, in particular areas on the surface, it was possible for them to determine that there must have been a lake there on the surface in this region. It would have been about, the scale bar here is 25 kilometers, so this is at least 50 and maybe 75 kilometers long and maybe 10 kilometers wide, so a large area of water there for a reasonable time on the surface. And the pH of that water, by drilling and doing the chemical analysis, it was possible to tell that the pH of that water would have been about right. So, you know, not too acidic, not too alkaline, for microbial life perhaps to have emerged there. So, you know, this is not actual life on the surface, but signs of the right conditions for life. So this was Grotzinger et al. in 2014. Okay, more recently still, so the Mars Express spacecraft again, that has a subsurface sounding radar on it, which is able to probe underneath the surface, looking for things like global maps of water, which can also be done with neutrons, but this is being done with a subsurface sounding radar. And so this paper in 2018 found signs of liquid water underneath the surface of Mars, near the South Polar region. And so this is the context on Mars for where that is. So here's the polar cap, which of course you can see in the images which we see from Mars and of Mars. But underneath the surface, the signs of liquid water. So this is amazing. So, and this is a cross-section here looking at these soundings underneath the surface. So about 1.5 kilometers underneath the surface near the South Pole, we have signs of a subsurface concentration of liquid water. So this might be kind of sandy water or something like that, is the idea. We can't really tell, but this was a result in 2018. Very exciting, showing that we have water not only in permafrost underneath the surface, but also in these subsurface lakes. These have been theoretically expected for a few years, but this is the first time they were seen. So just recently, actually, in September this year, so 3 more lakes have turned up. So again, with the same experiment, looking in the similar region on Mars near the South Pole, it was possible to see these. And so a paper in Nature Astronomy just a month ago or so showed this. So water underneath the surface. So water may have gone underneath the surface or did go underneath the surface of Mars. This is some of the evidence for it. Direct evidence, as I say, for water underneath the surface of Mars, and also in the frozen state as permafrost. And as I said, also this can be mapped with neutrons. So Mars Odyssey is doing that, and that is able to, that is a neutron detector. So the idea here is that you have a cosmic ray coming in, interacting with water, in particular with hydrogen in the H2O underneath the surface, and then you get a particular energy of neutrons coming off, which you can then map and find that there are a few areas near the equator of Mars where this technique is sensitive to the first meter or so underneath the surface, and we can see that there's those concentrations in the equatorial regions as well as near the poles of the water underneath the surface in the ice state. So, but also these concentrations of liquid water underneath the surface. So very exciting seeing that water there. However, I mentioned that Mars's magnetic field disappeared, and so that has allowed its atmosphere to disappear as well. So we think that there was a habitable atmosphere 3.8 billion years ago. So what I'm showing here is the different objects in the solar system and how they interact with the solar wind. So the solar wind, of course, is a stream of material which comes from the sun all the time, a million tons per second coming away from the sun. So as well as heat and light, which of course is necessary for life on Earth and anywhere else, the sun has a stream of material coming away from it. So the interaction with the Earth gives us things like the aurora, northern lights and southern lights, and of course up in Edinburgh you see that more frequently than we do down here. But of course the polar regions, northern Scandinavia and northern Canada, and also Antarctica and Tasmania, places like that, can see the northern lights and southern lights, and of course very dependent on the solar wind conditions as to whether these can be seen at low latitudes or not. But the solar wind in this image is coming from the left-hand side and interacting with the Earth. So this is our magnetic defenses, our magnetic field. The Earth itself is very small on this picture. So this is the so-called magnetopause, which is the boundary between the terrestrial magnetic fields and the magnetic field in the solar wind. Upstream of that is the bow shock. So that type of interaction means that our atmosphere is somewhat protected by from the solar wind, which would otherwise be able to scrape it away, scavenge it away. And also all these other magnetized objects are shown here as well. So Mercury, of course, with its magnetic field, shown here, much smaller than the Earth, but this also protects Mercury most of the time, although there are times, because that magnetic field is less strong than it is at the Earth, it's possible for the solar wind to actually push in the Mercury magnetic field, and we do get the magnetic field or the solar wind hitting the surface of Mercury sometimes. And you can also get meteors hitting the surface of Mercury, and we recently had a paper in Nature Communications about that, showing the pickup ions associated with a meteor hitting the Mercury surface, which is interesting. People could have a look at. Anyway, Earth has its magnetic field, and then going up in scale, of course, we have Uranus and Neptune, and then, which hopefully will be the subject of a new space mission in the future. We'll see, because so up to now we've only had Voyager passing and Pioneer passing, only Voyager passing Uranus and Neptune, but Pioneer and Voyager, and then of course Cassini and other missions going past Saturn and Jupiter, and indeed Cassini going into orbit around Saturn, and Galileo going into orbit around Jupiter. So these are relatively well explored by spacecraft, but you can see the enormous scale of the magnetospheres here. And this image here is just showing the size of the sun. This is the size of the sun as you would see from Earth, and comparing that with the size of the Jupiter's magnetosphere. So enormous. If we could see that in the sky, it would be very large. But we can't. So, but on the left-hand side, these are the magnetized objects. On the right, the magnetized objects. So Venus, Mars, Pluto, unmagnetized as well. And then comets, of course, we see comet tails. That's the other visible manifestation. The iron tail of comets associated with the solar wind. Of course, the dust tail more to do with dust and radiation pressure driving those tails away. But Mars basically is unprotected by a magnetic field. So the solar wind can get to the top of the atmosphere. Then the top of that atmosphere can ionize in sunlight or by collisions with electrons, etc., or charge exchange. So all of that can mean that you can get the Mars atmosphere actually escaping. So the Mars atmosphere has been escaping for 3.8 billion years since Mars lost its magnetic field. So now we have virtually no atmosphere on Mars. Venus, on the other hand, doesn't have a magnetic field either, and it is losing material as well at around about the same rate as Mars is losing material. So that must be being pumped up to, probably by volcanism, and certainly there have been large volcanic events in the past up to 500 million years ago. And there are signs now from Venus Express and from other missions that there's volcanism going on Venus, possibly to a smaller degree than it did up to 500 million years ago. But nevertheless, that could be what's pumping up the Venus atmosphere, because of course that is very thick. Okay, so the magnetic field is very important in keeping the atmosphere of Mars in, in keeping the atmosphere of the Earth in, but losing the atmosphere of Mars. And so that's what has been going on. So this is a graphic illustrating that. So missions like Mars Express, but also MAVEN here, have been looking at the Martian atmosphere and the escape to space. So this artist's impression shows that quite nicely. So this is the sun here, the middle of the solar system, not to scale, but basically the solar wind blowing out from the sun, then blowing past Mars and causing this atmosphere to escape. So we see increased loss during solar activity during the MAVEN mission, and also with Mars Express. So as I say, with Mars Express, we're still looking at this, and I've got a new PhD student who started working on this topic again. Okay, so Mars, we think, was very different 3.8 billion years ago to the way that we think it is, well, to the way that we see it now. So 3.8 billion years ago, it might have had the right conditions for life. So water on the surface, clouds in the atmosphere, continents perhaps. And so this is the simulations show that this is what Mars could have been like. Whereas Mars now, of course, much less alive, but nevertheless very interesting. And actually, recent signs have shown that there are some there's still interesting activity going on Mars as well. So naturally brings the question, was there life on Mars? So this time, 3.8 billion years ago, 3.8 to 4 billion years ago, is about the time when life was starting on Earth. So we think there could be a chance that life started on Mars independently at that time then. So there was some evidence from the meteorite Allen Hills 84001, announced in '96 by Chris McKay and colleagues from NASA, but most people find that unconvincing now. Here's the meteorite. Here's one of the electron microscope images from that. But any signs of life and biomarkers seem to be from the Earth's atmosphere as it went through the atmosphere and went to the Antarctic, landed in the Antarctic. That's the reason why we think that probably there was not life in this meteorite. But nevertheless, meteorites like this are able to give us clues as to what the atmospheric conditions were like. We know they're from Mars, for example, because of the nitrogen isotope ratios in them, which show there must have been the right type of escape from the atmosphere to show that they're from Mars. So we get different isotope ratios there in the different objects. But we think this, the bulk of the scientific community thinks this evidence is now unconvincing for life at that time. However, or for life in this meteorite. But we think 3.8 billion years ago, there's a good chance that life actually started on Mars at that time. So what do we need for life? There's a few things we need. We need liquid water, of course, as we mentioned, that's very important. We know that was there on Mars at that time from this direct evidence now. There's essential elements which you need, things like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. We need a source of heat, and we need enough time for life to develop. So we think all of those conditions were there on Mars, and may even be on the objects you saw at the beginning of the talk, even there perhaps now on those other objects like Europa and Enceladus in particular. So those are perhaps the top 3 locations for life elsewhere in the solar system. But as I say, Titan is potentially a possibility, and also maybe Venus is as well. So very interesting new result from Jane Greaves about the atmosphere of Venus. But these are the conditions we need for life as we know it. So this is just an illustration about Mars Express. So we're looking with Mars Express for water underneath the surface and in the atmosphere with other instruments on board. This is the subsurface sounding radar, which I mentioned before, and how it works. And we're also looking at the atmosphere and its escape to space. So the instrument on the edge here, this is the Aspera 3 instrument, which we're involved with, led by Sweden, but we've had an involvement in the electron spectrometer there. This on the top here is Beagle 2, which we tried to land on Mars, of course, at the same time, or just before Opportunity and Spirit were landing on the surface. And, a couple of years ago, Beagle was found on Mars. It very nearly worked, but it seemed to have unfurled 3 of its 4 solar panels, but not the 4th one. And so that would have been needed to send the data back to Earth. So we built the stereo cameras for that as well, and that we're waiting with Colin Pillinger and Mark Sims and so on for the data to come back from Beagle on Christmas Day 2003, but sadly it didn't come. But it was nice, though, a few years later to actually see evidence for that Beagle had landed correctly, but all it hadn't done was not quite being able to make the transmission back to Earth, which was a real shame. However, we're trying again, of course, with ExoMars, which is what we're talking about tonight. So Mars Express has found a number of exciting things on Mars, and one of those is methane. So this is trace concentrations of methane in the atmosphere of Mars. So only 11.5 parts per billion, so really trace compared to what is on Earth, for example. But Vittorio Formizano et al. Published this paper in 2004, and that confirmed telescope observations which had been made around about the same time. Why is methane interesting? Well, it should be very short-lived in the Martian atmosphere. In hundreds of years only, it should break up. So this is exciting because it shows there must be a source now. So this is either due to activity, which again, we had thought Mars was pretty dead, so that would be exciting, but also the possibility of life. That's possible that maybe life is even there now. So we have methanogens on Earth which produce this and live on methane. So this is something which could be very exciting. We can't tell from the data available which of those possibilities it is, which is why we have a special spacecraft now looking at this. So the ExoMars Trace Gas Orbiter, which hasn't actually seen any methane yet, but I'll get to that in a minute. But these are tantalizing results. Curiosity has sporadically seen methane. So first of all, they didn't see it at all. And then in 2014, there was a spike of methane, and then in 2018 it was seen again, and also recently there have been spikes of methane, which actually Mars Express has seen methane at the same time, but the Trace Gas Orbiter has not seen methane. So this is a bit of a puzzle as to why that's the case. But also in 2019, so oxygen was detected also in the atmosphere of Mars, again associated with this. So this is telling a story of, very interesting trace gases and something to look at in more detail. Okay, which brings us to the sort of current crop of missions to Mars. So at the moment we have the Trace Gas Orbiter in orbit around Mars, which was launched in 2016. So we have possibilities to launch to Mars every 2 years. So 2016 opportunity was taken by the ExoMars Trace Gas Orbiter. So this is the European Space Agency and Russia working together. That successfully got the Trace Gas Orbiter there. It reached its mapping orbit a couple of years later. Then there was the end of a dust storm, but it's now able to make very good measurements. And as I say, so far it hasn't seen methane, but it's made a lot of other interesting measurements. The Rosalind Franklin rover, which is what I'm mainly talking to you about tonight. So the image on the right-hand side. So this is the rover, the drill on the front. This is going to be drilling underneath the surface of Mars. There's our Pancam instrument at the top of the mast there. In the background, that's the landed platform called Kazachuk. So that has retro rockets on board to make it slow down before reaching the surface. So our rover trundles off that, and this is it. Artist's impression of it roving around the Martian surface to look for signs of life. So the launch date for that is now 2022, and it's been delayed a few times, including earlier this year for technical reasons, but also the virus thing didn't help, because it limited some travel, but it's mainly technical reasons that meant that we couldn't launch in 2020 like we had hoped. Meanwhile, NASA has InSight on the surface of Mars, so launched in 2018. That successfully got to the surface in November 2018 and is making measurements, for example, of Mars quakes. So this is not looking for life, it's looking at the interior structure of Mars using Mars quakes. So things like meteors hitting the surface, which make Mars ring. And so you can listen to that and find, basically find out more about the interior structure of Mars. NASA as well. So 2020 is a very, very busy year for going to Mars. Not as busy as it would have been with Rosalind Franklin as well, but nevertheless it is busy. So the NASA Perseverance rover, or Mars 2020 as it used to be called, was launched successfully, and so that's on its way. We're involved in one of the experiment teams for that as well, the Pancam Z team. So that will be actually caching samples on the surface for bringing them back later via a sample return mission. So this is the European Space Agency and NASA working together on that sample return mission to bring those samples back from Mars. So Perseverance can drill a few centimeters underneath the surface. It can't drill as deep as ExoMars, unfortunately, but nevertheless it can bring samples from the surface back, eventually, not Perseverance, but Perseverance is caching the samples in metal tubes, about 30 of them, to be left on the surface for bringing back by this later mission. Also in the 2020 opportunity, the UAE has launched its first mission, interplanetary mission. It's called the HOPE Orbiter, and that is going to be doing some atmospheric science. So that was launched in 2020. So exciting that they are getting involved in space science with the help of NASA, but they're doing it by themselves. I recently helped them with setting up a master's course in space science over there. We of course have our own master's course, and interesting to see the relationship between those. But nevertheless, so exciting times in the UAE for Mars exploration. Also, China has their first mission to Mars, and they're going to be so the orbiter. They have an orbiter and a rover also launched this year, and those will be all reaching the surface in the early part of next year. So something to look forward to with those missions getting to Mars, and of course with our own mission going in 2022. So very exciting time for Mars, and these are, we're looking for different things and different aspects. And the new thing about our mission, of course, is drilling under the surface up to 2 meters. I mentioned that harsh surface for temperature reasons, radiation reasons, and also oxidization. So we need to be able to drill underneath the surface, and I'll get to that in more detail later. Okay, so our mission has a payload on it, and so this is the payload on the rover. So on the left-hand side here, we see the context instruments. So Pancam, that's the instrument for which I'm the principal investigator. So this has a wide angle, 2 wide angle cameras spaced apart by 50 centimeters. We also have a high resolution camera. So this is setting the geological context and also doing some atmospheric science in the mission. So that's Pancam. And you can see the UK flag here, the UK lead of Pancam. And ESA basically being the host agency. So the next one is the infrared spectrometer. So this extends our mineralogy, which we can do in the visible with Pancam, out into the infrared. So this looks at one of the pixels of the high resolution camera and is able to contribute to the mineralogy. So Wisdom, a subsurface sounding radar. So that is very interesting as well. So using that using the radar technique, we can look underneath the surface in the first couple of meters. And this is for looking for rocky outcrops and places to drill, and also some signs of water underneath the surface as well. So that's very exciting. Hadron is the neutron detector, so a Russian experiment which will be doing what Odyssey is doing, but doing it on the surface and being able to map in great detail the neutrons coming off from the hydrogen just underneath the surface, so related to water. There's CLUPI as well. This is a close-up imager. So this, we're looking with the broad scale with Pancam, and then CLUPI is looking at the closer scale to be able to look at where we're going to be actually drilling. So in the drill as well, so the drill itself has a little instrument in it also. This is called MARMIS. So this is a tiny visible and infrared spectrometer actually in the drill tip. So we drill up to 2 meters underneath the surface to get our sample to bring it into the rover. But that MARMIS can get the local geometry for where we're getting the sample from. So the 3 instruments on the right-hand side here, these are in the analytical drawer. So this is the so-called analytical drawer. This is on the front of the rover and in the body of the rover. So we bring the sample up, having drilled underneath the surface, get the sample, bring it in and put it inside this analytical drawer. So this analytical drawer contains a visible infrared spectrometer, which is micrometer, French lead. There's also a Raman spectrometer, Spanish lead. So this is looking at fluorescence. and doing some geochemistry with that, again, to look at mineralogy. Whoops. And that went forward too early. But so the Raman spectrometer, Spanish led. The UK is involved in that as well. So Leicester University and also Rutherford Appleton Lab are involved in the Raman spectrometer. And that's there. And then the thing which we'll be looking for signatures of carbonates is and so on is the Mars Organics Mass Analyzer. So this is a gas chromatograph mass spectrometer, a little bit like the SAM instrument on Curiosity, which found those results which we saw earlier. But that will be able to look for the sort of chemical analysis, so looking for biomarkers. So we'll be able to look for a wide range of organic molecules with high sensitivity. It can also do chirality. So this is looking for left-handed and right-handed molecules. So on Earth, left-handed and right-handed molecules are very important for, used by life. So that's something which we'll be able to do on Mars for the first time on the surface with MoMA. So very exciting payload, and as I say, the focus is on drilling underneath the surface up to 2 meters, and so that's our plan. Okay, so this is a animation which I'll start in a minute about the Rosalind Franklin rover itself. So there's a lot of UK industrial involvement in the mission as well. The mission itself, the prime contractor for it is Thales Alenia in Italy, but the rover itself was led by Airbus in Stevenage, and so this is an image of the rover on the right-hand side, built by Airbus, and so some of our initial integration was done there. So as I say, the UK is very well represented on the mission, both from academia and from industry. So with this, of course, we're looking for life on Mars. The launch date is the 21st of September 2022. We have about a 2-week launch window to be able to get it off during that time. And our landing date at the moment is the 10th of June 2023. So that's the idea. We will drill up to 2 meters underneath the surface and with context and analytical instruments. So I'll just start a little video off here, which shows you about the rover and its structure. So the drill at the front here, Pancam, of course, at the top of the mast, the 2 other cameras here, the navigation cameras, that's a high resolution camera. The Wisdom antenna at the back there, you can see the solar panels. And this, of course, is the drill. So the drill in this animation has got a sample. So it puts that into the analytical drawer here, and then we can also image that with the cameras on the top of the mast, as well as with the CLUPI, the close-up imager, and that's the way the sequence works. So solar powered, which means that we have to land somewhere near the equator because of the angle of the sun. So that limits us to where we can land, but that's fine because there are some really good scientific targets there. And just to show you the size of the rover, so this is some of our science team, which we were meeting in ESTEC, before social distancing times, of course, back in December last year. So some of the team here for the Pancam team. So here's Pancam at the top of the mast, and just to give you an idea of the size. So we're sitting with the cameras 2 meters above the surface. The cameras, the wide angle cameras, are 50 centimeters apart, so this gives really good stereo reconstruction for getting the 3D situation. I hit that too early. The 3D reconstruction with the stereo cameras very well. This is the high resolution camera where we can we can look at rocks very closely, effectively a telescope on the top of the mast there, and then this is complemented also by the high resolution camera. So the noisy thing coming up, this is the an animation of a parachute test going on. So I'll click this. So this was from 2019. So you've got to have really good parachutes to land on the surface of Mars. And one of the things which delayed us was the fact this parachute wasn't deploying properly. But these are showing correct deployment of the parachute, which was redesigned before this test. And this showed that it worked pretty well. So some further work on the parachutes is going on at the moment. And in fact, we're about to have some more parachute tests going on out in Oregon. We're hoping for some high altitude drop tests involving the parachutes. This, for ExoMars, is the largest parachute ever to be sent to Mars, so it's very important that it deploys properly. It has a 35-meter diameter, so something which is important that it works well. Okay, so I'll try and advance. Okay, so why do we call this rover Rosalind Franklin? So this was made actually by a competition run by the UK Space Agency. And they got something like 36,000 entries into the naming what to name our rover, but the winning one was Rosalind Franklin. And the reason for that, of course, picture of Rosalind Franklin on the right here. So she was a brilliant X-ray crystallographer, and she took this amazing image, photo 51, of a fibre of DNA which helped Watson and Crick's discovery of the double helix. And so this image here, this is some of her lab notes. She did other important work on the structure of carbon and indeed viruses, of course, very topical at the moment. But you know, this is why it's called Rosalind Franklin, because we're searching for life on Mars, and this was fundamental to the discovery of the double helix, so very exciting. So hopefully our photo 51 on Mars will show something similarly exciting. We'll have to wait and see. Okay, so the reason for drilling, as I hinted at earlier, is because we're getting below where we can the sort of harsh environment on the surface. We have to get below where a couple of things go on. So first of all, where ultraviolet can penetrate to. So because of that thin atmosphere on Mars, ultraviolet basically bathes the surface. So we need to get below at least 1 millimeter to get below that. Get below about 1 meter to get below oxidants associated with the surface material, and then below about 1.5 meters to get below where ionizing radiation can get to. So this gives us the best chance of finding biomarkers in the Martian environment. By drilling 2 meters underneath the surface, we're below where this can get to. So I had another PhD student a few years ago looking at the ionization, you know, the ionizing environment underneath the surface of Mars, and below 1.5 meters is right for that's, you have to drill at least that to be able to see good biomarkers on Mars. Okay, so that's our plan, to drill underneath the surface, a subsurface, to a rocky outcrop to get a sample and put that in the analytical drawer. Okay, so what about our landing site? I mentioned we're constrained by engineering reasons to land somewhere near the equator, but that's fine because that's between these low areas and high areas on Mars. And Oxyoplanum is the site which has been selected for ExoMars. So we had a number of workshops involving a lot of people from the UK involved in selecting the you know, and of course Europe and Russia and everywhere else as well, trying to get a good landing site. And we narrowed it down eventually to Oxyoplanum. That's what we can do with the combination of engineering constraints, but also scientific interests. And this is an interesting site because it has, from orbit, you can see the signs of clay-bearing rocks there, which are about 3.9 billion years old. So it's the right sort of age. There's also remnants of a fan or delta. This is near the output of Cocoon Vallis on Mars, in this particular region on Mars. So you can see this is a very exciting area to land. So what's shown here is the landing ellipses, and this changes. These are the landing ellipses for this 2022 launch opportunity, when we're sending the rover to Mars. So this changes a little bit as the days go into the launch window. That roughly 2-week-long launch window starts off more equatorial like this. So over this summer, with the entire team, we've been helping to map the surface of Mars in this region with new images from the HiRISE instrument on Mars Reconnaissance Orbiter, for example, to put this into context and get the geology as well as we can before landing, because some of this area had not been mapped in great detail before. So we've had postdocs and PhD students and lots of people involved in the mission, basically involved in this mapping activity. Okay, so a bit more about Pancam. So this is the science eyes of the Rosalind Franklin rover, and so there's a cutaway diagram shown of it here. So as I say, the 2 wide-angle cameras are shown here. These are 50 centimeters apart. This is the electronics associated with them. In front of each of those, we have a filter wheel, each of which has 11 filters in it. So this is to get the different colors of light. We've chosen those wavelengths very carefully to be able to get good geology and atmospheric science on Mars. This is the high resolution camera. So there's a mirror here. The light goes in through this focusing mechanism to be detected on the image plane here. So our detectors sit basically in the cameras. So these are the things which make up Pancam. We have filter wheels, the 2 wide-angle cameras. So each of those has a filter wheel associated with the monochrome detector. We have a high-resolution camera which sees in color. We can put red, green, and blue filters, of course, to get color from the color images from the WAC data as well, but HRC already images in color. We have a Pancam interface unit, so this is the electronics at the back here, a DC-DC converter, this is for the power to convert the rover supplied power to the power that we need for the instrument. All this is housed inside an optical bench. So the optical bench is shown here. That sits at the top of the mast. We also have these so-called small items. So these are small but important because these are our calibration target, which has different colors here, fiducial markers, and for basically getting the shapes right. So the fiducial markers sit on the rover here, and with that we're able to measure those in detail to get the scale. We also have a little rover inspection mirror, which is able to look underneath the rover to see what's underneath there. So that's sort of in case there's any obstruction. So this is sort of for engineering reasons. So with this, we can get stereo imagery, we can get colors, we can get shapes and scales. And this is just a little bit for who was involved in actually producing these. So our lab, UCL's Mullard Space Science Lab, which normally we have about 200 people working there. A lot of those are working from home at the moment, but the engineers doing the future missions are there and working. So about 25% of the normal workforce, but that's our lab. So what we did was the filter wheels, the Pancam interface unit, so this electronics, and also the optical bench itself. Thales Alenia and Switzerland did the wide angle cameras, and the high resolution camera was done by our German colleagues. So the German DLR and OHB in industry working with them. But the small items done in Aberystwyth. So these are manufactured in the UK again. So, and here's some of the science team here at a meeting showing the size of our optical bench. This is a 3D print. Here's the so-called small items, Matt Gunn holding those. That's our colleague from Aberystwyth. Again, some of the science team involved here. And this actually is Pancam just before it was delivered last year. So 20th of May last year, it travelled around the M25 around London to Stevenage to be delivered. And this is our project manager, Mary, here, who led the last couple of years of the mission towards delivery of the Pancam, and some of the engineers involved. So Barry and Craig and Tom and the others all involved in that important delivery. Okay, so our science team is international. We have 9 nations involved in the science team, which are indicated at the bottom here as well. So this is one of the instruments, and of course it's international, and these are the science team involved. Okay, so I love showing this slide because it has the actual filters which are going to be looking at the surface of Mars, and these are the surfaces which will be looking at Mars. So here's the left filters and the right filters, and each of these filter wheels, as I say, in front of the wide angle cameras. These are the wavelengths and the widths of these. So we can see the relatively wide ones here for red, green, and blue. These are carefully selected filters to look for water-rich minerals and to minimize the error in the determination of water-rich minerals. So we had another student, Claire Cousins, who's actually now in St Andrews, so a little bit up the coast from Edinburgh. So she's a senior academic there and has a team working on that as well. But she, as a PhD student, helped us to actually select the filters, the water-rich minerals, to identify the water-rich minerals. We also have solar filters here, the very narrow filters, the solar filters to look for water vapor. So the absorption feature of water at 935 nanometers, and we're looking at continuum close to that, and other features in the water absorption spectrum. So we'll be able to look at a sunset on Mars and determine how much water there is between the sun and us. So that goes into atmospheric models, so we can see how much water there is in the atmosphere. That leads eventually into atmospheric escape. So this is a very important area of the science for me, as well as, of course, of the geology, which we have a big team involving people around the UK and internationally, as you saw on the previous slide. Okay, so the high resolution camera provides rock texture. So that's, as I say, the bit which is looking in detail at the rocks. Okay, so this is some more images of the instrument. So this is a blow up of the camera system, and this is what it might look like on Mars. So our colleague Helen from Aberystwyth did some really nice animation visualizations showing what it looks like on the top of the mast. And here we have the two wide-angle cameras and the high-resolution camera. This is the infrared spectrometer, and these two are the navigation cameras, which are the rover cameras. So ours is the science camera. Okay, so this is just an example of some of the uses of Pancam. So Aberystwyth have an emulator, and we have some other emulators in the team as well, but this one has been used in many field trials, and this is showing some of the images from those, the types of things you can do. So obviously getting good 3D maps of the area. So this is one of the things we're doing, looking at the area near the rover. And the geologists have been able to add dip and strike to these. So this is looking at sedimentology and trying to link up those areas. We can also do geology to look at composition. So this is looking at ratios of the various filters which I mentioned, and so with that we're able to distinguish minerals and using principal component analysis. So this was from a field test in Iceland a few years ago. So we've done a number of tests on Earth for this, and this is another one done in the Utah desert in 2016. So this gives you an idea of the quality of the image we'll be able to get back from the from Mars. So this, of course, is Earth. You know, the sky is blue. There was a truck just off to the right of this, and which you can't see on the image, but we know it's Earth. This is not Mars. But once we get to Mars, we'll be able to get amazing images. But Matt Baum, who's now our co-principal investigator from the Open University on Pancam, so he was the science lead for this trial in the Utah desert, and we've had other trials as well. This was another trial in the Atacama Desert in February 2019. So these are all Mars analog type of sites on Earth. So with some of the geology and some of the conditions as they are on Mars, and some mineralogy similar. And here's an example. So Elise, who's also working at St Andrews with Claire, was doing this mineralogy using the filter data. Okay, so this is a little video showing the sequence of the mission just before it lands. So we'll just run through this quickly. So this is what happens as we approach Mars. So the trace gas orbiter relays the data back to Earth. So this is the descent module going through the atmosphere. And with heat tiles to stop it burning up. Then the parachutes deploy, the back shell eventually is released, and then the rover on top of the landed platform, the Kazachuk, floats down through the atmosphere. The retro rockets fire, and this stops it hitting the surface too hard. And there's the rover on the top, landing hopefully correctly on the surface. Okay, so once it starts deploying, here's the solar panels which are starting to deploy, giving power. And further solar panels. Of course, that's very important to do that on the first day to get the power into the batteries for keeping it warm overnight. So then Pancam deploys and the rest of the instruments on the top of the mast and scans the surface. So we decide from this which way to drive off the rover platform, landing platform. So this happens much quicker, much slower in reality than it's being shown here. We have a number of features, including wheel walking, so you can see the wheels basically being picked up there to avoid possible rocks on the surface, with some autonomy on board to mean that it doesn't hit rocks. And then eventually it finds a place to drill. So drills underneath the surface, 2 meters underneath the soil to bring a sample up. And so that, whoops, that stopped before it was supposed to, but anyway, so hopefully this is somewhere near the right position. If not, we can just, yeah, actually we can go on. Okay, so, right, I think the computer didn't catch up with that. But anyway, the rest of the video shows the sample being distributed to the various instruments. Okay, so this shows some of the integration going on at our lab of Pancam. So this is Pancam here. So some of the electronics about to go in. You can see a wide angle camera and its filters there. This is an inside picture of Pancam. So showing in our clean room, of course, before the lid was put on. So here we see the 2 wide angle cameras, each of those with their filter wheel in front. Here's the high resolution camera, the focusing mechanism, and the image plane. So this is the flight one, which is now on the rover, and this is the one which is intended to go to Mars. So this was delivered in last year, installed in August last year. Around about that time, we had a press release with ESA about the rover, the filters on Pancam. So these are the colors of the filters. So these were at delivery to us before they were put into the optical bench, and showing the filter colors. And this looks a little bit like contact lenses. So for the general public, these were contact lens, effectively contact lenses being put in front of the Pancam, the eyes of Pancam, and again some pre-delivery pictures. So this is amazing to be able to show this. Again, this is the completed rover going through its tests at the end of last year. It's now going through more tests. It's now in Cannes in France before it goes back to Turin for some more tests. These particular tests were done at a facility in Toulouse. You can see Pancam on the top of the mast here, and the solar panels and the drill and everything there. So this is the flight optical bench of Pancam, and that's of course where it sits there on the top of the mast. And here are the small items and where they sit on the rover. So this is our picture showing the integrated Pancam on the rover. Okay, so this was actually the mast installation going on. So this is in the clean room, seeing Pancam having been installed on the top of the mast, this was great to be able to see this. And then our colleague Matt Gunn from Aberystwyth showed basically a piece of paper with some writing on it to Pancam. Of course, this is done all in planetary protection conditions. We have to keep everything really clean in order to send it to Mars, and so this was in the clean room at Airbus. And here's our first light picture on the rover. So as you can see, it says "Hello Mars." Okay, so our first light image on the rover in August last year. And so it was great to be able to see that. Okay, so this is the way the mission is going to go. So the launch, September 2022, travels to Mars. So every 2 years we get this opportunity to launch to Mars, and so that's our next opportunity. So landing on the 10th of June 2023, as I say, at 15:32 UT. So that's the time and date for your diaries, and that's the position of Mars at launch. So that gives you an idea of the mission. Okay, so just very quickly, this little video gives you a bit more information about our contribution to Pancam.
Pancam is a panoramic camera. That's what it stands for.
Pancam, this is the scientific eyes of the Rosalind Franklin rover. So we're looking at the scene on Mars, trying to do some geology, trying to do some atmospheric science.
The instrument is a fairly plain white box, essentially, but it's what's inside the box that's interesting.
We've packed as much science as we possibly can into what is basically a camera system.
We have 2 wide field cameras on the ends.
Stereo imaging cameras of the wax, one at each end. So on a stereo baseline of about 500 millimeters for stereo imaging and plotting of routes on the Martian surface. So looking at what's in front of the rover and working out where it can go.
So each of these wide-angle cameras has a filter wheel in front of it with 11 positions, and we can move that around to look at the different colours of the light coming from the surface of Mars. And so with that, we're able to not only build up a colour picture, but also to look at composition of the rocks, in particular looking at the light which is reflected from the rocks, to look at the minerals in them, and to look particularly for water-rich minerals, because of course we're looking for water and life on Mars.
And then we have a high resolution camera.
So the HRC light path comes in, goes, hits a fold mirror, goes through a focusing mechanism in this area, and then projects onto a sensor down at this end.
This will enable us to actually see fine-scale, small-scale details on the Martian surface. For example, texture on rocks, or it will enable us to see single grains on the soil, and that's very important for the geological investigation of the surface.
We were PIs on the optical bench, and we produced the PIU and DC-DC converter, and they were built here.
We already delivered the hardware, so it is now in still finish in Airbus. Now they're putting all the things on the rover. The project starts since 2004. So what we're talking about is 15 years of our life is working on it.
I remember the first time I saw part of Pancam and then got to handle some of it. And it was a pretty amazing experience to think that, you know, things that you've touched and helped with will hopefully be on Mars soon.
It would be a fantastic discovery to actually be able to find evidence for life anywhere else on the universe, and Mars is the nearest place we can look, and so our rover mission is specifically designed to do that. Okay, so that's the video. So the last thing is just a summary. So ExoMars 2022, I haven't updated this slide, will provide an important new dimension on Mars, drilling underneath the surface. So Pancam with the other context instruments provides geological and atmospheric context. So these are the contact details and the Twitter thing. So thank you very much for listening.
Well, thank you, Andrew. That was absolutely fascinating insight into what's coming on. Perhaps people could unmic and thank you in the normal way. We do like to be traditional. It made me feel very old, though. I worked on a mass spectrometer. Mag and I worked on a mass spectrometer in the late 60s, and we had a wardrobe of electronics and a transit-sized instrument. The thought that you're now putting this in a drill tip shows how things have moved on. But excellent. And we can have some questions. Peter, over to you.
I had one myself, if I could ask you, Andrew. Thanks for a great talk. There was a recent NASA mission where they tried to hammer something into the surface. And I was wondering if any feedback from that helped you with thinking about the drill.
Well, yeah, so this is InSight. So this is a thing which has seismometers, which is listening for the Mars quakes, but also it had a mole, which was a little bit like the design of the mole on Beagle 2, which had that got there successfully would have been the first to do that. But yes, this was trying to get underneath the surface. So that did not work very well, it has to be said, in the first case. So they tried to move it, and I think it's working better now. So that is, it basically is a mole. So there's a magnetic thing which kind of hammers away to try and get the thing under the the surface. But what we're doing is drilling. So it's directly drilling with this Italian drill to drill underneath the surface. It's got several lengths, I think 4 different stages to the drill, which you're putting 0.5 meter lengths together, which is why it's not, you don't have a complete big 2-meter drill on the front of the thing. There's also a spare for anybody that's done drilling at home. It's good to have a drill spare. So and that has been tested in a range of environments and hardnesses and things of the expected range. So yes, it's very useful to have previous missions which are given information. I mean, the information actually from that mole was too late to be able to do anything much about changing the design, but it's actually using a different technique. So we're very confident that it will work in the range of conditions expected, and that's still expected to be the case. But thanks for the question. Yeah.
Neil, are you there?
I am indeed, yes. Thank you, Professor. It was a fascinating talk. Who doesn't love hearing about Mars? So my question is that we've deployed so much in the way of science to Mars. Does that make it easier or more difficult when we try and corroborate results?
Well, I mean, corroborating results is definitely an international endeavor. So there've been a lot of rovers and, all American so far in terms of what's worked on the surface of Mars. We were so close with Beagle 2, though. That's very frustrating that we didn't quite make it with Beagle 2, but nearly did. I mean, early on, I think there was a couple of Russian missions which did send back some data as well. But there have been a lot of orbital missions, so we're sort of building up a picture about Mars, and there's something called the Mars Exploration Program Group, which looks at international plans for Mars and tries to get people to fit their research together. I mean, it's obviously, we're edging towards, we're finding water again and again in different ways on Mars, and finding out that water was indeed involved in shaping the Martian surface we have now. Now we're looking for life, and we're aiming to bring samples back. So these missions are doing different but complementary things. So it's like the UAE mission. I mean, that has been harmonized with what everybody else is doing. But also it's great to send missions elsewhere in the solar system. So as I mentioned at the start, I mean, JUICE, we have that going to the Jupiter system. Very exciting mission for the future as well, where we're going to be able to look at Europa and Ganymede and Callisto, and Ganymede in great detail, and that is one of the jewels of the Jupiter system. It has its own magnetic field, so that's going to be very exciting to look at. Meanwhile, also missions to Venus are popular as well in proposals at the moment. We'll see about selection of those quite soon, I think. That's not, I don't know whether a Venus mission will be selected. They're all in competition at the moment, but also missions elsewhere. So it fits in with the overall realm of missions which we're doing. So these types of missions, we can explore the solar system, of course, in detail and be able to understand that. But of course, the astrophysics missions help us put all that into context. And by looking at life and whether it developed elsewhere in the solar system, that can tell us more about extrasolar planets and what may have happened there as well. So there's of course several missions in the extrasolar planets area, and of course James Webb Space Telescope about to hopefully be launched in I can't remember what the launch date is now. I think it's a year or two's time. But that also giving a very exciting. So all of these missions are very important, but there's something to me about being able to go to the surface of Mars and see whether life ever started there. And that could be our first indication of life elsewhere in the universe. But of course, all the other missions are trying to do the same thing. But we have the best chance, I think, with the ExoMars Rosalind Franklin rover, and then with the sample return mission to Mars later on as well. I think with those missions, we hopefully will have an answer. But that's not to rule out answers with other missions. As I say, the phosphine result from Venus is fascinating as well.
Okay, thank you very much for that. Mark had a question about technology aging.
Thank you, Andrew. That was a really fascinating talk. Really enjoyed that. I've worked on projects in the past where they've had such a long life that by the time you actually get to launch the project, the technology is so far out of date. The video said it started in 2004. It's 2020 now, and the technology of CCD sensors, CMOS sensors, whatever you're using, is quite different from what it was then. How are you keeping the technology up to date, or is it actually really old?
Yeah, I mean, it is fairly old. I mean, you know, we wrote the proposal for this in 2003. You know, before Beagle was even launched. You know, and so that we were already thinking about the next step. We selected the detectors in the late. Well, yeah, I can't remember exactly which year, but probably about 08, 09, something like that. So it's. But what we do, you know, is put together the science we want to do with the mission, and with space technology, of course, we have to be able to have something which we know is going to be able to work in the environment. So it's got to have the right heritage in terms of radiation testing and temperature testing and all that type of thing. I'm sure you're very familiar with, but yeah, I mean, it's true that if we were going to be starting again now, we'd probably have a detector about double the size. It's a 1 megapixel CMOS sensor, but what we do though is put the scientific what we want to do with the science and the resolution that we need. That's the important thing, to be able to get that, the signal to noise ratio that we need, of course, for the sensors. So we've got something which is good enough for the science that we want to do, and so the design is frozen then, and we build the instrument, make sure it will work, go through all the testing, etc., etc. But yes, you know, if we were doing another mission to Mars starting tomorrow, I'd be proposing a bigger sensor than we have at the moment. But this is fine for the science, and the combination of, in particular, of the wide-angle cameras and the high-resolution camera and the Kloopy gives us a good range of imaging that we're able to do, and that's good enough. The SAM instrument, or at least the MOMA instrument, which is based on SAM, they've of course learned lessons from that and been able to adapt things as well. So we have made some adaptations as time has gone on, but we've stuck basically with this this well tried and tested CMOS sensor, which we know is going to work well.
Okay, thank you for that. Oh, there's a few more coming up all of a sudden. I think Carl was next. Carl, do you have a question? Hello, Carl.
Yeah, I'm just trying to, sorry, thank you very much for the talk, Professor. That was really very interesting. I think you've answered a lot of my question was about the drill.
Oh, yeah.
When Peter asked you initially what you would do, I think you answered most of my questions. And during your presentation, I could see there's a lot of other things happening. You're not just sort of, if the drill doesn't work, you have a lot of other things, a lot of other interesting instrumentation.
Yeah, but of course the main science that we want to do is indeed with the drill to get the sample from underneath the surface. So it's a very important part of the mission. But yes, there are certainly other things we can do. But we're you know, the testing has been done with the drill to make sure it will work. We have several different segments, as I say, and a spare. You know, we hope that we're covered to get enough drill samples. There's I mean, on to the subject of the drill, there's a limited number of samples we can actually do and analyze on the surface. So only there's I think a few times we can do a vertical survey, and then a couple of times we can actually drill down to the 2 meters. So we have these context instruments to decide exactly where to drill, and so we will be using that range of evidence to decide on a good place to be drilling. So this will give us
okay. Andrew Mackey has 2 questions. Cheeky boy.
Hi, you're so good to me. Excellent talk. Thank you very, very much. 2 questions. In relation to the 3.8 billion years since the atmosphere was being lost, how did that compare to the entire age of the planet? And secondly, do you expect surprises in the geology of the surface? You seem to know a lot about what you expect to find. You know, is the lava going to be sort of the thick stuff, or is it going to be the runny stuff that gives you seas on the surface? What do you expect, please?
Okay, yeah, so the 3.8 billion years, so Mars is 4.6 billion years old. So 3.8 is relatively early in the history. So it's at the end of what's called the late heavy bombardment era, when lots of stuff was moving around in the solar system and hitting things, including the thing which caused that Hellas Basin on Mars. So it's quite long, quite far back in Mars's history, is when this time was, and so that's the time the magnetic field was lost, etc. So that's and as I say, that's the time also 3.8 to 4-ish billion years ago. That's the time that life was starting on Earth. So if there is any life on Mars from that time, it would be very simple types of life forms, and those which we'd be looking for. So the second question was about the geology and what are we going to see that's we're going to see anything unexpected. So yes, from orbit we have very poor resolution maps. Of course, landing in a particular place, you will see very different things. And so so while broadly we have the idea that there are clays and water-rich minerals like that on the surface, we don't know the fine structure. We can see, the best we can do from orbit is maybe 30 centimeters or something like that in terms of the size of things. So we will get much better resolution on the small scale. So we don't expect any big surprises, but the details of exactly where rocks are and where to drive and where the sort of local features are, that's the type of thing. And then putting that in context with the orbit images, that's what we're going to be able to do. And the key thing, deciding where to drill, that's what we can do with these very small scale images to be able to do that. So as I say, we've set up the science requirements of the instrument and the performance of the instrument to be able to deliver on that, and to give us good spectra and to give us a good range of resolutions with which we'll be able to make those decisions. So the operations will be done in an operation center, hopefully in Turin, if we're operating like that. I know that the Mars Perseverance rover is going to be all done remotely because of the current pandemic. Whether we're still in that in a couple of years' time, hopefully not. So the idea is to do this in Turin, but we're also setting up to be able to do it remotely as well at the end of the mission. But so those are the types of things. So hopefully I answered the question.
Okay.
Excellent. I think we've got time for one more, Peter, and then we'll.
Yeah, I think Will, was your question, has it been addressed?
If I could just ask a very quick question, would that be okay? Or is
Sure. Carry on.
just with the drilling there, Professor Coates, absolutely amazing, really great presentation. I'm actually very into drilling, so I'm just wondering if you're planning on drilling down and actually taking a small core sample in a sealed package to send back. Are you able to do test drills? And then when you decide to take to actually capture your samples, is that going to be the kind of almost disposable bits that you have to use, keep the package and then send back in a sealed kind of way?
Well, yeah. With this mission, what we're doing is drilling, getting a sample and analysing that on the ground on the rover. So we're not bringing that particular sample back. Okay. But the other mission, Perseverance, is going to do that. So that is going to drill, get a sample, and put that in a metal canister ready to bring back to Earth. But our mission, yeah, we're going to analyze it on the surface. But yes, we can do test drills and test, the sort of cohesion and things like that, and to make sure that we're drilling in the right place. And yes, we get a core sample from 2 meters underneath the surface, bring that into the rover and analyze it, and that's what and send back the data by radio. But as I say, the other mission, Perseverance, is going to be is going to be caching the samples in different locations at Jezero crater, which is their landing site, the later mission will bring there'll be a fetch rover, hopefully built in the UK as well, and that will search around for these sample containers to bring those back ultimately on a rocket. So that is a very complicated mission, as you might imagine, because you've got to, first of all, land Perseverance safely on the surface of Mars, do its drilling, leave the canisters around. Then the later mission to go to have something in orbit ready to send the data back, and also to dock with it. So then to go down onto the surface, get these sample containers back into orbit, send it back to Earth, and land safely on Earth for analysis in labs, which hopefully some of those will be in the UK. So the people that do that type of work are really excited about getting those samples. It's one of the sort of, you know, grails of this type of thing, to be able to get a sample back from Mars, which we know where it's from. I mean, we have meteorites, but we know roughly where they're from, but we don't have all the context which we will have from the rovers. So that's a really exciting thing. But the drilling bit, yes, is certainly a very important aspect of it. And so test drills, yes, are very important.
Excellent. Thank you very much.
Over to you, Andrew.
Thank you. Again, can we thank Professor Coates for this great talk. I think we understand much more about the mission. Great context as well.
Thank you very much.
Great. And can I? Somebody's not muted. I think. Okay. Can I ask Alan if you'd like to share your slides, and we'll go through the sky in November.
Right, can you see that?
No. Not yet.
Right. Wait a moment. Hey, look.
Yes, I can see you.
Can you see the Sky November first slide?
No.
No, okay. Let me go back a stage. Unshare. What do I unshare? Truth. Share. And it is invalid. Okay, try this. Share. How's that?
It looks like it's coming. Yes, I see a couple of sea creatures.
Yeah, I'm getting there.
That's it, Alan.
That's it. Sorry about that. Yeah.
All
okay.
right, no problem.
Right. Thanks, Andrew. Okay. Sorry about the hiccup there. If you read my Sky November note on the ASE website or in the newspaper this month, you'll know that all the planets are visible. Two of the most interesting two, though, are Mercury, which is making its best apparition in the morning sky, and of course Mars, which we've been hearing a lot about. Let me turn on the laser. Right, can you see that? Yes. This is a view from Stellarium with the artwork turned on, showing Mars crossing the meridian later this evening as Orion climbs up in the east and Cygnus and Aquila fly off into the west. But let's look at the night sky charts that appeared with my notes, showing the two hemispheres of the sky looking north and looking south. In the northern sky, we have the plough below the pole star Polaris turning counterclockwise and in fact reaching well up towards the zenith by dawn. Across the pole from the plough is Cassiopeia, the W, which is overhead at these times in the evening. And the summer triangle is toppling over into the west. That's the triangle formed by Altair, Deneb and Vega. While in the south, we have the square of Pegasus leading off into Andromeda, and of course the galaxy M31, the famous Andromeda galaxy, now quite high in our evening sky, very high, at its highest, in fact, in our evening sky. Over in the east, Taurus is there with the Pleiades, and just climbing above the horizon at these times is Orion. And the two planets marked on the chart, well, one is Saturn down here low in the southwest, quite close to Jupiter, but at these times Jupiter is just below the horizon, Saturn is just above it. And coming up towards the south, we have Mars, which is of great interest, of course, still. As far as the sun goes this month, this shows sunrise, sunset and twilight times for Edinburgh. For November, using Dominic Ford's inthesky.org website. The sun's continuing to move south, so the sunrise is getting later, an hour later during the month, and meantime the sunset is getting earlier, an hour and a bit earlier during the month. Twilight times are also changing, getting late earlier in the evening, and so by the 30th it's effectively dark by 17:17 well, actually December the 1st, it's effectively dark by 17:17, about 5:15 in the evening. The moon, here are the phases for the moon for November. Full moon on the 31st, that was the hunter's moon. It was the first full moon after the harvest moon. And the next full moon is right at the end of November, the 30th of November, and then we have a penumbral lunar eclipse. And of course, the middle of the month, for the fortnight around new moon, we have darker skies for looking at fainter objects. Here's that eclipse. This is the last of 4 penumbral lunar eclipses in this year. It's happening as the moon goes through the penumbra of the Earth's shadow, the outer, fainter shadow of the Earth, as opposed to the dark umbra of the Earth. It's an eclipse that lasts from 7:32 in the morning to 11:53 in the morning of the 30th of November. But in fact, actually the moon sets for Edinburgh at 8:14 GMT. So we have only a few minutes to view it before the sun, we have only a few minutes to view it before it's set and the sun's risen. So I doubt, since it's not going to get very far into the penumbra, I doubt we're going to see any darkening of the moon on that morning. There's the map of the Earth with the regions in which it's visible or not visible. The darker area here, covering most of Europe and Africa, is the region for which the moon is entirely below the horizon during the eclipse. We're of course here, so we see just the eclipse happening at moonset near sunrise. If you're in Hawaii, you've got the entire eclipse visible, and it's nearly overhead in the middle of the eclipse. This is again from Dominic Ford's website, showing a band around the equator of the sky and the ecliptic, the path of the planets, of the sun rather, and also the region where near where the planets stay during the course of the year. The sun this month is moving southwards still, and so this region around it, around the sun, of course, is the region that we can't see because of the sun, of daylight. The evening sky lies to the east of the sun, and that's where we find Jupiter and Saturn. To the west of the sun, we have Mercury and Venus. Jupiter and Saturn down here, and that's the views on the 16th of November, the relative view sizes of the 2 planets. And by that date, in fact, Saturn's rings span a distance which is just slightly larger than the total diameter of Jupiter. So they're both quite wide through a telescope, but Jupiter is smaller than it was a few weeks ago. Mercury, I've mentioned, is emerging in the morning sky. On the November the 1st, it's probably too faint at magnitude 1.5 to be seen, but by now it's getting up to negative magnitude, so it's quite bright, low down in the morning twilight. And by the end of the month, or by the 26th, it's still there, but getting lower in the twilight. It lies below and to the left of Venus, and those are the images, those are the diagrams of Venus for this month. All these planet sizes are accurate relative to each other. So you can see the relative sizes of Venus in the morning sky to Jupiter and Saturn in the evening sky. Venus is fairly constant at magnitude -4, so it's brilliant in the pre-dawn. And finally, Mars has been through opposition. Opposition was on October 13, 14 last month, and it's now receding and fading, but it's still very much worth looking at. Turning to the north at 8 o'clock in the evening on November the 16th. These star positions are also correct for these times. So an hour later, November the 1st, and an hour earlier by December the 1st. And by December 16th, this chart could still be valid, would still be valid as far as the stars go at 6 o'clock in the evening. Here's the plough, and the W of Cassiopeia is overhead at these times. Andrew Farrow took an image of this region of the sky, the northern sky, on October the 13th from calendar, and as happens when you've got lots of stars in the sky, it's sometimes difficult to pick out the brighter ones from the fainter ones on a photograph. I'll outline the stars of the plough on there. And of course, Mizar and Alcor, the famous double star, is in the second star along in the handle of the plough. I mentioned that back in September, and it's one of the ASE 24 objects of interest that you'll find on the ASE's website. Turning west at these times, well, the summer triangle is sinking down. Here it is in the western sky, pointing more or less towards where Jupiter and Saturn are setting. There's lots of interesting objects to look at, as I mentioned many times, in and around the summer triangle. You've got the Ring Nebula in Lyra, you've got the Double in Lyra, you've got the Dumbbell Nebula in the square in Vulpecula, you've got the Cotanger asterism also in Vulpecula, the double star Albario in Cygnus. Lots of interesting things. One object that Ian Smith photographed this month, though, lies northeast of Deneb, and it's a faint nebula called the Cocoon Nebula. And he posted a picture to our Flickr group. This is a wonderful photograph. This is an object, a star formation region. It's around 2,500 light years away. It's not unlike the Orion Nebula in that it's, except that it's about twice as far away as the Orion Nebula and a good deal smaller intrinsically. It's a dark cloud of gas and dust in which new stars and planets are being formed, and it's being illuminated by massive young stars. Inside it, the center star in the nebula here is only about 100,000 years old. We wind the clock back a couple of hours. Excuse me, I'll clear that. Yeah. If we wind the clock back a couple of hours, this is the view looking south at 6 o'clock in the evening in the middle of the month. And at that time, it's still dark. You'll see the summer triangle a good deal higher in the southwest, pointing down to Jupiter and Saturn. Jupiter is around 9 degrees higher this time, and Saturn's 1.5 degrees or so higher in the sky. A close-up of that region shows Jupiter and Saturn. This is on the 1st of November because I wanted to plot the paths of the two planets during the month. Both of them are moving towards the east, northeast. Jupiter is moving more quickly, and by the end of the month, it's almost where Saturn is. On the 1st, Saturn moves half the speed, so the separation is halving during the month from about 5 degrees at the beginning of the month to only 2.3 degrees by the end of the month. By December the 31st, they pass within 0.1 of a degree in a spectacular conjunction, but it'll be low down in our evening twilight. I showed this frame a little bit earlier, showing the brightnesses and sizes of the two planets. And the moon is going to be near them on November the 19th. This is a little insert showing the two planets' positions on the 19th of November and the moon below and to the left of them both. And if you look at the moon on that night, then that's the view that you'll have of the moon. A faint glow of earthshine on the darker hemisphere, and the bright crescent with Mare Crisium, the famous impact basin on the moon. It's 556 kilometers across, which is about the same distance as from Edinburgh to London. This is south at our 20 hours GMT on November the 16th. And here we have Mars in the middle of, coming up towards the middle of the southern sky. And the square of Pegasus, Andromeda leading off it from Alpheratz at the top left corner of the square. And if you go along one star, bright star, and then make a left, you get M31, the famous Andromeda galaxy, 2.5 million light years away. Visible on a decent night to the naked eye, but very easy to see through binoculars. It's going to get brighter, of course, because it's approaching us, and in 4 million years' time, it's going to collide with our own Milky Way system. Back to Mars, it's in the constellation Pisces. It was in opposition, as I said, on the 13th, 14th of October, closest to us a few days before that. And it's now receding. This month, it recedes from 70 to 96 million kilometers. And I showed this slide earlier too, the relative sizes of the planet on the 1st of November and the 1st of December, and you can just about make out the tiny button of the south polar cap. A good deal smaller than it was a few months ago, because the southern hemisphere of Mars has been enjoying high summer. It's moving slowly, Mars in Pisces. In fact, it's stationary on the 25th when its motion changes from going westerly to heading off towards the east. And Mark Phillips has produced this montage of images he's taken of Mars, with some of the features annotated there, including one he obtained last night, showing Mars, and showing, you can also notice that the southern polar cap has been shrinking since this photograph was taken in September to the beginning of November. As Professor Coates mentioned, the lower areas in the southern hemisphere are largely, sorry, this is I should say Mark's image is upside down, so that the southern polar cap is at the top, and the brighter areas on the planet are, of course, sandy, dusty deserts, and the darker areas are higher, more exposed rock and slightly darker. On the 25th of November, Mars will be above the moon in the sky, and on that occasion, that's what the moon will look like on the 25th. And before we leave this area, there's a few other things I want to mention. Mars is not the only planet here, because two other planets are in our evening sky. You'll need at least binoculars probably to see them, or a telescope. Uranus and Neptune, the two most distant planets. Uranus was at opposition in Aries on the 31st of October. Neptune over here is less than a degree to the left of the star Phi Aquarii, which lie around 10 degrees below this group of this pattern and circle of stars called the Circlet of Pisces. That's the relative sizes of the planets on that day. Mars 17.3 arc seconds across, and Uranus and Neptune a good deal smaller. In fact, the distances are also different. Of course, Mars is 82 million kilometers away on that day. Uranus is 2,817 million kilometers away, and Neptune 4,417 million kilometers away. In reality, both these planets are more than 7 times wider than Mars, and about 4 times wider than our planet, the Earth. I said I'd got a few more things to mention. One of them is the star Mira in Cetus, the whale. Mira, the name means wonderful. In fact, it varies quite considerably in brightness. It's a long period variable star, a red giant that pulsates in size and brightness over a period of about 332 days or 11 months. It lies 300 light years away. At its brightest, its average is about magnitude 3.4, about as bright as the faintest stars in the Plough. At its faintest, though, every 11 months it dips down to around magnitude 9.3, so you'll need a telescope to see it. It has been known to brighten to magnitude 2, in fact, to rival any of the stars in the square of Pegasus or the Plough. The light curve, the recent light curve is shown here. You'll see this. This is today, or just about today down here. You'll see it's recently reached a maximum of almost magnitude 3. It's now starting to dip, but it's got a good way to go before we lose it from naked eye visibility. If you look at it through binoculars, you'll notice it's very red. It's a red giant, a very noticeably red star. This is a false color image by NASA's Galaxy Evolution Explorer, which obtained these images of Mira. Mira lies in both of them, this end of this tail, almost like a comet. The Galaxy Evolution Explorer, its main study was the history of star formation in the universe. These images were taken in the far UV, the shortest wavelength, ultraviolet, and this is a, let's say, longer wavelength image. The shed material, which has been driven off the star as it evolves, is lagging behind as the star moves through our galaxy at 130 kilometers a second through the interstellar medium. This tail it's leaving behind is something like 13 light years long. Looking east, these times at 20 hours on the 16th, the Pleiades is in the middle of our eastern sky, above Taurus and above Aldebaran in Taurus, and the top of Orion is beginning to appear. You've also got to the left of Orion, you've got Gemini with Castor and Pollux, and to the left of the Pleiades, you've got Auriga with the bright star Capella. But I want to concentrate this month a little bit on the area around Perseus, which lies above and to the left of the Pleiades and below Cassiopeia. That's the region I'm going to look at, and there it is in closer up. The brightest star in Perseus is this star Murphak, which is magnitude 1.8, so it's as bright as the brightest star in the Plough, but whereas the stars in the Plough are about 100 light years away, Murphak is 590 light years from us. It's a yellow-white supergiant star. Its surface is just a bit hotter than our sun, but it's 60 times wider than the sun, and it's got a mass of around 8 times that of the sun. It may also have a planet, but that's been unconfirmed. It's an unconfirmed planet, perhaps 6 or 7 times wider, larger or more massive than its Jupiter. It's the brightest star is Murphak in a cluster called the Alpha Persei moving cluster, which is easily visible through binoculars. That's a picture of the moving cluster. Murphak is this star here. This cluster is also called Melot 20 or Colander 39. There are several other open clusters in clusters of stars in Perseus, and also down here in Auriga. In fact, I noticed recently Mark Phillips has put an article about the features in Auriga on our website. You can check the ASE website for more information about those. Not done with Perseus yet. I want to mention another star of interest, and that's this one, Algol, a variable star, one that fluctuates in brightness, but not because it pulsates like Mira. It's an eclipsing variable star. Its name comes from, there's the details about Mira. It's an eclipsing variable star, about 90 light years away from us. It varies between magnitude 2.1 and 3.4, quite a noticeable variation to the naked eye. Every 2 days, 20 hours, 49 minutes, it dips down from its normal magnitude at magnitude 2.1 down to magnitude 3.4 as one of its stars eclipses the other. The name comes from a demon's head in Arabic, and with its neighboring stars, it represents the snaky head of Medusa, one of the Gorgon sisters, and the head of Medusa was used by Perseus to turn the sea monster Cetus, in which Mira is a star, turned the sea monster Cetus to stone before he rescued Andromeda. The variation of this star was first noted by an Italian astronomer in 1667, but its regular variation was first identified by John Goodricke in 1783. It wasn't known whether it was due to eclipses or a star spot. And the variation, in fact, may have been known to the ancient Egyptians. Now, John Goodricke was an English amateur astronomer who was deaf, and in fact, he attended a school for deaf pupils in Edinburgh at one time. Thomas Braidwood's Academy was the first school for deaf pupils in Britain, as far as I know. Goodricke was also credited with several other discoveries, including the period variation of Delta Cephei, which is the prototype of Cepheid variables, which are extremely important in measuring intergalactic distances. Sadly, Goodricke died in 1786 at the early age of 21. As far as Algol itself goes, this is what's happening. You've got 2 stars in orbit around the common center of gravity, and when the brightest star passes in front of a fainter one, you get a small dip in the total brightness, But when the opposite's the case, the brighter star is hidden by the fainter star, you get a larger dip, and these eclipses last for around 10 hours. And if you want to look at eclipses this month, I've put the times of minimum of algol for November and December here. These are times for convenient eclipses. So on November the 16th, there's a mid-eclipse at 2 o'clock in the morning. The night of the 15th to 16th is a good one for looking at algol's variation, as is the night of the 18th to 19th. And these are the times also for December. This is the view looking south at midnight, a bit later in the evening at midnight on November 16, 17. Mars by this time is over in the southwest, and Orion is well visible in the southeast. As we know, the belt of Orion points down to the brightest star in the sky, Sirius, and upwards towards Aldebaran and the Pleiades. And if you continue that line a bit further, you'll get to Algol. Mars is sinking in the southwest, and it will be setting in the west-northwest before dawn. On November the 18th at 5 o'clock in the morning, this is the view between south and southeast. Orion by then is in the southwest, and Mars will have set by then. Climbing in the east is Leo, and the sickle of Leo, this backwards question mark of stars above Leo's main star, Regulus. And I've timed it for them because that's when it's expected that the peak of the Leonids meteor shower will occur. They diverge from a radiant point that lies in the sickle of Leo. But of course, meteors, you can see them in all parts of the sky at all brightnesses. And in fact, the shower is active for not just that morning, it's active over quite a long period. According to the BA handbook, it's active from the 6th to 30th of November. But in fact, most of the activity is concentrated in the few days between the 15th and the 20th of November. The meteoroids originate from comet Tempel-Tuttle, which was last at perihelion, its closest point to the sun, back in 1998, and it's not due to return in 2031. And we tend to only get major showers of Leonid meteors in those years when the comet is nearby. So at the moment, its rates are expected to be quite low, maybe 10 or 20 meteors per hour. But the ones you see will be very quick. Leonids are about the fastest meteors we get each year, 71 kilometers per second. They're only visible, of course, when the radiant point is above the horizon, and the radiant rises down here or over in the northeast at around 22 hours. So don't expect to spot many Leonids until after midnight. They're mainly a morning. It's mainly a morning shower. This is the view looking south at 6 o'clock in the morning. We're now shifting to the morning view. And by that time, 6 o'clock in the morning, in the middle of the month, Leo is in the south. And Orion is sinking down in the southwest. Venus, though, is now brilliant in our eastern sky. This is the view looking east, and there you see Venus quite close to the star Spica in Virgo, with Mercury below and to its left. The plough by then is high up in the east, tail down, climbing high into the east. And we, as you know, we can use the handle of the plough to Arcturus, the bright star in Bootes, and spike to Spica. But arc to Arcturus, spike to Venus doesn't have the same ring. But that's the situation in our morning sky. The view on the first, this is 1 hour before sunrise. Mercury just becoming visible. In fact, it's probably too faint to see on the first. You may have needed to wait a day or two longer for it to be bright enough to see. Venus is about 20 degrees high, an hour before sunrise. And I showed this earlier, showing the appearance of Venus during the course of the month. The change in the appearance of Venus is during the course of the month. It's moving around the far side of its orbit, getting smaller as more of its surface and more of its gibbous disk is visible, but its magnitude is staying quite steady. Mercury, on the other hand, is changing in its appearance quite quickly. Initially, as it emerges from the sun's twilight, from the twilight, it's a thin crescent, but quite small, getting smaller though, and and shrinking to 5 arcseconds across by the 26th. I reckon by about the 26th is probably about the last morning you're likely to see it before dawn. It's furthest from the sun, 90 degrees away from the sun at its so-called greatest elongation on the 10th. That day it is 13 degrees below and left of Venus. So very, you can use Venus as a very convenient finder to finding Mercury before dawn. On the 13th of November, again 1 hour before sunrise, Mercury, Venus and the moon, crescent moon, not quite between them, but not far away. That's the moon on that morning. Slender crescent, 5.6% sunlit and brightly earthlit. And earthlight, of course, is light reflected from the Earth, which is almost full in the lunar sky. On the next morning, on the 14th, the moon 6 degrees below left of Mercury, only 1.4% sunlit. But if it's a good clear morning, there's a chance to spot it before sunrise because it rises 91 minutes before the sun. And that's the view at 1 hour before sunrise at the month's end. And Mercury by then is probably too low down to be spotted before dawn. Now, before I finish, I've just got one other thing to mention. That is that before the month's end, if we're lucky, the Chinese may have launched another space probe towards the moon, Chang'e 5. Launch, I think, is scheduled for about November 24th. It's a very ambitious mission. It's a lunar sample return mission, a similar flight profile, in fact, to the Apollo missions. What happens is that a body, the orbiter with further modules are attached to it, go into orbit around the moon. The top part descends down to the surface. It drills down for up to 2 meters to collect samples from the below the lunar surface. Transfers the sample to an ascent module, which blasts off from the moon's surface and rendezvous with the orbiter that's remained in orbit. It docks with the orbiter, transfers the sample to a return capsule, which returns back to Earth. That's the hope. They're hoping to get about 2 kilograms or so of lunar material back to the Earth. The target for the landing is a region called Mons Rumca in Oceanus Procellarum, the Ocean of Storms. And that's where the Ocean of Storms is on the moon. And that's where Mons Rumca is. It's a region, a volcanic formation, a mound around 70 kilometers across with numerous domes in it, which are very small shield volcanoes, lava having upwelled from below the surface. So that's the target for this Chang'e 5 mission, which should be launched later this month. And that's all I got for you this time.
Well, thank you, Alan.
Thank you.
Well done as always. Thank you very much. We've certainly got some dates for the diary. All we need now is those weather windows, which we've been a little short of, I think, in recent weeks.
Right.
Okay. Well, I guess that wraps up tonight's agenda. I hope you've all enjoyed it. Unless anybody's got any parting shots. Mark usually hasn't eaten yet, so we'll not keep him from his food much longer.
No, I have eaten tonight, thank you.
Oh, right. Well, you can talk at your house.